Today's talk, of course, is going to be about fuzzing. It is my passion to delve into the fuzzing research, and I will warn you ahead of time, this is a long slide deck, so I'm going to move fairly quickly. And I originally did write this for a keynote at Woot this year to a small group of academic researchers, so it's pretty heavy on kind of the state-of-the-art of where fuzzing is. So before we get started, can I just get a raise of hands for people who have ever used a fuzzer, ever at all? Okay, wonderful. About half of you, maybe. And can I get one more raise of hands if you have written a custom harness or your own fuzzing tool? Beautiful. Okay, great. Yeah, so that's about 20% of the people in the room, and that just shows how fuzzing is growing and its impact. And hopefully today we'll learn a little bit about where things are going. So I'm going to be walking through 3 different sections where we're going to focus on how instrumentation has changed to improve fuzzing, how the academic world has looked at the different ways to generate data more efficiently, to get deeper into parsers and targets, and also how the execution runtime loop of fuzzers has changed into different environments that allow us to target different layers of code that wouldn't have been available 10 years ago. I currently work at Eclipsium and do trainings through Fuzzing.io. And this is a follow-up to a keynote I gave about 4 years ago where I discussed everything that happened from the coining of the term fuzzing in 1991 all the way up until about 2013 with the release of the first real production-ready coverage-guided fuzzer called AFL. And at the time, I was commenting on how that really sparked a revolution in fuzzing because fuzzing was very hyped in the early 2000s. People started applying it, but then bugs kind of started drying up a little bit, and we had this kind of movement towards manual auditing and reverse engineering, and people lost some faith in the capabilities of fuzzing. So it wasn't until a technological innovation came along that really allowed it to become much more useful, and nowadays it finds the most bugs per year as a single technique. So of course the Renaissance, we're in Italy, so excuse it's a little cheeky for me to be referencing, I suppose, the classical era, but this started the Renaissance, and now I think we're in this new era, this age of discovery, where most of the vulns are being found through fuzzing. So I referenced this tool, AFL, if you're not familiar with it. It's a tool that was released in 2013 by a well-known researcher named Michael Zawiski. He was at Google for quite some time. And the main innovation here was the ability to not only provide mutated data. So fuzzing, if you're totally unfamiliar, is a way to provide inputs into a program that is intentionally malformed and corrupted. And if you do it millions and millions or billions of times, those corruptions may uncover actual parsing errors, and that will lead to crashes. And so there's 2 approaches. You can take a input that like a normal document or a normal file that would be parsed by this parser and intentionally corrupt it, or you can go read the spec for whatever that input is and create a grammar that describes how to construct that type of input. And the problem is when you do it manually, it's much more effective, but it's very time consuming, it's error prone, you need an expert, specs are incomplete, the documentation doesn't always match the code, and so on. And so mutational approach overcomes the manual effort, but originally there was no feedback signal, so it was just blindly corrupting inputs. There was no way to make incremental progress over time. And so in 2013, that problem was solved by being able to collect code coverage at very high speed and incorporate it in the feedback loop. So you knew that this little corruption caused new behavior in your target program to execute. It may not be a crash yet, but it is somehow different than the last time you ran an input through the program. And again, if you do this over time, you slowly crawl the program graph and you generate a set of inputs that collectively can exercise more of the code. So AFL started the revolution because of good engineering, high performance coverage. It also had a number of basic features that had been aggregated over time, things like using constant tokens or keywords that might be part of the inputs, things like that. So with that as the starting point in 2013, here we are 10 years later. What has happened since? Well, you may have heard that Google has been investing a lot in fuzzing over the last decade, and as of early this year, Cluster Fuzz had reported finding over 27,000 different bugs in Google software, which included 8,900 vulnerabilities. So there's bugs and there's vulns. Fuzzers will find both. Vulns are just ones that can be taken advantage of for security relevant purposes. And at this point, actually, if you go on Google's GitHub to their OSS fuzz, I have 850 projects here. I believe they crossed the mark of 1,000 projects this summer. So Google is for free fuzzing 1,000 different open source projects. Anybody can go, if you're a code owner, you can go sign up and get free fuzzing resources from Google. And it's very effective. And of course, they're using a fuzzing approach that is similar to what AFL was using. So that's just showing that it's in production. Now, when the AFL came out, it caused this huge explosion of interest in the academic world. If you look at all of the top 4 academic conferences, I would say maybe 10 to 20% of the papers that have been published there the last 5 to 10 years have been somehow related to fuzzing. And it wasn't until 2018 that Michael Hicks, who's a professor in the US, kind of looked at all these papers that came out and realized that there really wasn't good science happening. Fuzzing is a complicated interaction between several components, and so it's hard to really distinctly determine that your change and your innovation is causing a significant impact. And that really comes down to not having good evaluation criteria. And so he wrote this paper that had the conclusions that basically in almost every paper that had been published the last 5 years, the evaluations were not good and ultimately led to misleading assessments of whether or not that was a valuable progress. And so they enumerated several different issues there. You can read these slides later for more details, but ultimately it was a notice to the academic world, hey, we need to get better about how we're evaluating our fuzzing. And essentially, here's a graph of some related academic papers. This is showing the influence of that evaluation. So he's saying we need better evaluation criteria. And so the academic world went to work and started to think about that problem and came up with a couple of solutions. Google developed something called FuzzBench, which allows you to run a number of different fuzzers on the same target software, and then collecting the statistics of code coverage over time and bugs found and crashes generated, things like that. You can rank order, you kind of have a tournament of competing fuzzers, and they can be scored in their effectiveness. They can be graphed for their progress against a specific target, and along the x-axis is showing which fuzzer is better at this particular target. Then there's different ways to look at the coverage over time. If you look at over a longer campaign, you want to look at it in log scale, et cetera, et cetera. And if you are going to fuzz a new target, you might go look at the FuzzBench for if there had been a similar style of parser or a similar style of program that was fuzzed before, and determine that, for example, on the right-hand side, we have curl, and HongFuzz happens to be a better curl fuzzer in these experiments than perhaps AFL++. But if you're fuzzing SQLite, AFL++ happened to be the better fuzzer. So depending on your target, you may be able to develop some intuitions based upon these benchmarks. And then that was followed up with just a couple of years ago with additional work from Google. You hear their name a lot in fuzzing because they really are investing kind of the most resources in it. And Fuzz Introspector was developed as a result of needing to determine not only how much coverage do we get over time, but where in the code, what are the blockers, are we hitting the complex code where a lot of logic exists and bugs are likely to be. And so this is kind of like a code cov from, like gcov from GCC or LLVM that allows you to get breakdowns of, which functions did we reach, what's the code complexity of that function, are there, what blockers might there be there, how many other functions does this particular function dominate in the call graph and things like that. So, because if you're not able to solve paths in a particular function, then that's what we start to call a frontier edge, where it's blocking progress into a large portion of the target program. So we have the ability to measure, and then we need to, determine what should we be measuring against. So there's the fuzz bench set of targets like the SQL and curl and anything on OSS fuzz really. And then also over time, as we've observed the capabilities of coverage-guided fuzzing, there's certain problems that are harder for brute force mutation to solve. So for example, if you have a 32-bit magic value, you're still brute forcing and trying to flip bits to generate that value, so the odds of doing it is quite low. Let's see here. So why is all this focus still on fuzzing? We might think that, well, if we just want to fuzz the old code because old code is bad, but Google, in fact, tweeted a couple of years ago that 40% of the bugs that are found by OSS fuzz are actually regressions before the code is reshipped. So what this means is that developers are they're making the same mistakes, they're reintroducing similar errors that they've discovered before, and it's the cluster fuzz and OSS fuzz inside of Google that's capturing those before they actually get shipped. And so there's all this focus now to move fuzzing not only for security researchers to attack third-party code or targets of interest, but to put it into the CI/CD pipeline, put it into your DevOps chain, and so on. So the tech moved into the compiler, and now there's a fuzzing engine that sits inside of LLVM and comes with it, and all you have to do is add a couple of flags to enable fuzzing. And now at this point, it's also on Windows. There's automatic fuzz generators for Go and Rust and so on and so forth. And then there was the problem of fuzzing traditionally was a native code kind of strategy. You're targeting native code looking for memory corruption bugs. But what if we have high-level languages, web languages? Most of the software being developed these days exists online in microservices and different environments than native code memory corruption. So people at Code Intelligence developed a fuzzing tool called Jazzer to target Java. And we've just seen that kind of influence. And now anything that runs on the JVM, there's Python fuzzers and so on as well. And there's some examples here you can look at later for what those look like. I mentioned OSS fuzz. One interesting thing about OSS fuzz is not only can you see example harnesses for other targets, you can also see whether perhaps a standard developer may not realize that there's certain strategies to doing fuzzing efficiently. So perhaps the harnesses that do exist are missing some testing that you could come along and add yourself. And if you do that and you contribute to OSS fuzz, then they'll actually pay you a bounty for improving their fuzzers. And if those fuzzers find vulnerabilities, they'll pay you the bounty on the vulnerabilities as well. So if you're interested in fuzzing, that's a great place to start. So AFL gets talked about a lot because it was the first major progress point 10 years ago. And then eventually that became kind of stable, and it was picked up by some other researchers, Andrea Fioraldi, Mark Hess, Dominic Meyer, and was continually improved with new instrumentation, new backends, new capabilities to solve branches in code in a better way. So right now, if you're getting into fuzzing, the first place to start is typically AFL++. And then you have to realize that there's 100 different environment variables that you can set that turn on different modes of operation. And you can sit there and use the same type of fuzzer for years and unlock more potential and find bugs and new targets, even though other people have used AFL to fuzz targets in the past. Some of these examples of things that have been added are, LAF Intel, CompCov. I think I have another slide coming up on this, on what those particularly are. But they're compile time modifications to the code that make the code more fuzzable. And once you graduate past AFL++, especially if you're a Rust programmer, you may come across libAFL, which is a modular system that more or less encapsulates all of the academic progress over the last 5 years or more. All of the things that have shown success in individual experiments have now been re-implemented and put into a pluggable system where you can decide that I want this type of code coverage and this type of instrumentation, and I want it to run in an emulator, or I want to use compiler-based instrumentation, whatever it might be. So extremely flexible and powerful. I really encourage anybody who's going to write their own fuzzers to come here because that's more or less limitless in how you can apply it. Okay, so let's talk about these instrumentations a little bit. Fuzzers need to know when a fault occurs. So typically memory corruption was the target because obviously your program crashes, and if your program terminates, well then you know you found a problem. But you guys have probably heard of this bug, heartbleed. Now this is one of those bugs that was found shortly after the development of libfuzzer being put into the compiler, and so there was a lot of interest in this high-profile bug and whether or not fuzzers could find it or why they hadn't found it. And it really comes down to the fact that, well, if there's no crash, then we need to add some sort of other checker into the target that validates some properties to determine whether or not a memory safety consideration has happened. And in this particular case, if you don't recall, the heartbleed bug was reusing a buffer. And so you could have other memory contents that were filled from a previous request returned to you. And if that has private key material or things that are sitting in the OpenSSL memory, then that can be a problem. And so in order to address this, they literally had to write something called address sanitizer. And this is the ability to provide shadow memory and some bookkeeping and metadata about every byte of memory. And it puts memory into certain zones and isolates things so it can determine if you're reading out of a buffer that you shouldn't be able to access at this time. So at this point, we have a number of checkers. They can find all these different bug classes for native code. There's also now undefined behavior sanitizer around the corner, and is being added as the hardware-assisted address sanitizer. So features are being put into your CPUs that are working in, working with the compiler in order to be able to capture bugs and determine that some sort of memory security error has happened, safety error has happened. And sanitizers are now in all your main compilers. So GCC, Clang, and Visual Studio all have address sanitizer support in them. It's another compile time flag. And if you use address sanitizer, then these fuzzers are also enhanced with the knowledge of address sanitizer. So libfuzzer, AFL++, and HongFuzz can use the type of coverage information that is provided by the compiler. So then we come to this problem of we need to do different instrumentation because I mentioned those magic values, 32-bit values, or a series of constraints that are going to be difficult to brute force your way through. And traditionally, the approach to that was to apply very heavyweight engineering with symbolic execution, congolic execution, to take the path through a program and represent it as an algebraic formula, very, very long algebraic formula, and then pass it to a specialized calculator, really, that is designed to solve algebraic constraints. But this is a very expensive process, and when we're fuzzing these days, we're talking about executing 10,000 times a second sometimes, and so we don't really want to delay and spend a large percentage of our compute on a solver when empirically, the results are that if you just put the compute effort into brute forcing, over time with coverage feedback, it tends to solve these problems. So what we can do is make the problems easier to solve by splitting those 32-bit comparisons or 64-bit comparisons into sequential 8-bit comparisons, right? So normally if a compiler is going to check if you have a 4-byte magic value at the beginning of your file, the file magic, it's going to look at that whole 32 bits at once. But instead, when we compile our target code, we can ensure that the compiler splits that into check the first byte, then the second byte, then the third byte, and the fourth byte. And so instead of 1 in 4 billion chance, you get a series of 1 in 256, right? So it's 4096 over time, or 1024. Okay, so then beyond that, so that's splitting comparisons. Then there's also the potential ability to compile two different versions of your target. And when you find that there is a constraint, or it's checking for a value to go down a code path, you can spin off a second execution that is basically going to modify every byte of your input and determine whether or not that led to a change in the comparison value that's in the code currently. So you're trying to bypass this constraint, and you more or less kind of brute force each byte to determine this offset influences the value that we're seeing in memory that's being compared. And so then it can drill down and focus on that. So rather than having to use a complicated solver, it's using a gradient descent kind of approach, input to state. So this is called Red Queen. It's very powerful, and it's really solves a lot of problems that fuzzing normally wouldn't be able to solve. Okay, so then input generation. Ultimately, this comes down to grammars. If you can define the specific structure of your target, then you want to kind of make sure that you're mostly providing correct input with only a small amount of corruption involved. And the real problem there is that grammars have existed since the beginning of fuzzing, really. It's been a manual effort, and they didn't have a way to combine the grammar with a feedback either. So if you're generating grammars or you're mutating grammars, you still want the feedback on whether or not that modification is valid or providing progress. And so rather than mutate the generated input, for example, you can actually, if you have your grammar in a graph, like an AST of sorts, you can mutate the graph itself and then generate new inputs. And you want to know if that mutation to the graph was effective. And another approximation is, of course, you can just extract constants from the binary in the parser code itself and use them as part of what you're fuzzing with. So, the magic value you may know is being compared somewhere in the code. You don't know where in the input to put that magic value, so you just kind of spray it around and hope that at some point it lands in the right offset of your input to provide progress in your target. And if you want to do complex fuzzing of a language parser, such as a DOM or a JavaScript engine or something like that, then of course you need grammars to generate the linguistic semantics that are necessary, as opposed to just the binary bits that you would normally be flipping. There's a powerful DOM fuzzer called Damato that uses EBNF. You can come look at this later. It's extremely flexible. You can apply it to any other target space as well. It doesn't have to just be a browser fuzzer. You can fuzz PDFs with it, and it's up to you to develop the grammar. And then developments beyond that. Now there's Fuzzily, which is a fuzzer that is specifically for JITs, and it mutates the intermediate language representation before it gets JITted. A very complex but powerful approach. And if you're targeting something that has protobuf as a serialization layer, then there's an adapter to libfuzzer that will automatically be able to fuzz protobuf definitions. And so if you're fuzzing anything that Google writes, basically anything that uses gRPC or in the browser, whether it's the sandbox broker or the network parser layers, they're all using protobuf. And so that's a way to get an easy grammar definition because they're already available. And of course, syscalls are just an API between userland and the kernel, so syscaller is another approach. But then there's the fallback that, in the end, if you have to, you can use solvers. And there's been progress specifically to create solvers that are for fuzzing, so they're high performance. They tend to take compile time attributes or instrumentation and add them into the target. And at this point, these are all built into AFL++ and libAFL as well. SymCC and SymQemu, SymQemu in particular can target binaries that's high performance, and you can run it adjacent to your normal fuzzing. So it will just look at the inputs that your fuzzer is generating, randomly select them as it becomes available, as a CPU core is available to do another iteration of solving, and we'll try to solve whatever the constraint was that was blocking that particular input. And now there's a couple of brand new ones just in the last year. SymSan, I believe, doubled the performance, and so it's actually state of the art. Triton from Quark's lab, folks released a higher level API that allows you to integrate it with fuzzing fairly easy. It's still being evaluated at this point, though. So the next thing we want is we want to open up the ability to target new code, right? So it's easy. When AFL came out, it was designed as a file parser-based fuzzer. You could generate inputs via standard in to your targets, or you could modify a file, write it to the disk, and then pass it as an argument to your target. So the initial proof of concepts were against command line parser utilities or simple wrappers for libraries that would exercise the APIs from a command line utility that would read in from standard in or files. And as people wanted to apply this to things beyond files, like network protocols or kernel system calls or ioctls and things along those lines, we needed a new technology to come along. And at this point, syscaller has been in production since, I think it's on the next slide, but syscaller has found 2,046 kernel bugs found and fixed. And that was in 2019, so now we're up to 45, 35, so thousands of bugs a year, almost, basically. An average of 2 or 3 bugs per day since the release of syscaller, which is pretty phenomenal. So this is showing that if we develop and continuously fuzz an attack surface, then we're continuously finding bugs over time. We need these in our CI/CD pipelines because they're preventing regressions and so on. And all this development tends to happen in the Linux and open source space because, well, number one, we have source code. And in fact, it was when AFL was first released, it was only using a really simple instrumentation for source code targets only. And this solved the problem of performance because running targets thousands of times per second is a hard problem. You need to optimize for how to do that. And if you're collecting code coverage, you need to figure out how I'm going to instrument every basic block in this binary without adding a breakpoint to every basic block or some sort of interrupt that will slow down the target significantly. And so in Windows, it's kind of like the anti-POSIX environment, right? We don't have forking, which is typically the way that you can quickly spawn new processes on Linux, especially with copy on write. Also, operating systems these days have ASLR, and one thing that we need to do is compare the execution of a program over time. So 2 different executions of a program, if ASLR gets in the way and moves your binary around, well, how are you going to compare 2 traces and determine if new edges have been uncovered? And so that's a problem. Then, of course, almost all programs are multi-threaded, especially if they have a UI. File system resources are locked by default, and so when you open a file, you have exclusive access to it unless you pass a flag. There's a number of different types of IPC, and COM gets in the way, adds asynchronous behavior, adds wait loops, and all kinds of just jitter into every program. And also Windows is a very handle-based architecture where if you're going to be accessing a type of resource in the operating system, you tell the kernel that and it gives you a handle. And it's different than a file descriptor, even though we use it kind of similarly. It's more complex and tends to have locks and sharing considerations on the kernel side. So how do we fuzz Windows? Well, the first kind of solution is we can use something called DBI, or Dynamic Binary Instrumentation. And what these look like is basically, it's kind of like a layer of a JIT where you're jitting from native code to native code, but you want to intercept every instruction the first time you execute it so you can modify it if you need to. So essentially what a DBI does is it will load your program itself manually and then mark those pages as non-executable. And so then it will tell the program to start running. And of course, the first thing that happens is it tries to execute non-executable code. That causes an interrupt. The program handles it, and it says, OK, you're starting to execute this code. We're going to copy this basic block somewhere else and allow you to add code coverage tracking or whatever instrumentation you like. So that was the first approach. There's a number of tools that do DBI. Dynamo Rio is a popular one. Frida supports multiple architectures and is popular in the mobile world. And debuggers can be used to implement these approaches as well, since all you're really needing to do is cause an interrupt so you can disassemble the code and modify it, and then it will run native speed afterwards. So the real problem with DBI tools is that I've mentioned, on the Linux side, we're talking about running things in the 5,000 to 10,000 iterations per second per core. On the Windows world, we're talking hundreds to maybe 1,000 or 2 executions a second, and that's due to the instrumentation. And when we're talking about brute force, the number of iterations really does matter. We're talking about a 10 to 100 time difference in performance. So how do we get past that if DBI isn't the solution? Well, and also the other problem with DBI is we can really only target userland code because we need to be able to generate and trap exceptions and modify code. It's extremely difficult, if not impossible, to do this in the kernel space. So the solution comes to snapshot fuzzing, where we'll take a memory snapshot at a point in time in the program that we're interested in, and we will then emulate or somehow accelerate the execution on that snapshot in KVM or something along those lines. And this is currently the most flexible approach because you can take a snapshot from anything. You can take a snapshot via JTAG or GDB stub off of a device. You can take a snapshot from a kernel debugger attached to Linux or Windows, and so on and so forth. So that is currently a place that we see a lot of innovation and people migrating is how do we do snapshot fuzzing. It does require kind of expert users to use this level of tools. This is highly sophisticated. This is not going to go in your CI/CD. But if you want to find deep bugs, perhaps you want to take multiple snapshots at different points in time, and these are at different state transitions in a protocol, for example, then this just has the ultimate flexibility. But you yourself are going to be writing essentially an extension to an emulator, and at this point that's going to require sophisticated engineering. But for example, last year, the next slide. So the one tool that I would recommend if you want to get into snapshot fuzzing is called WTF Fuzzer by Axel Souchet or Overclock. And this one was originally designed for Windows targets, but can also target anything from GDB stub. And the idea here is you just implement a few callbacks that allow you to move fuzzy data into memory where typically the pointer was expecting, file input or network packet or whatever it might be. And I used this last year to do fuzzing on the Microsoft's, the Windows eBPF implementation. It's a new part of the kernel. It implements the analog to what is on Linux for network-based eBPF hooking and instrumentation. And so I was able to fuzz the ioctl layer from Windows, executing a series of ioctls over time and using this fuzzing approach. So until that point in time, until WTF came along, fuzzing Windows kernel is a very difficult attack surface to approach. Basically, you've got WTF, or you have this other tool called NIX, KAFL, which is using things like Intel processor trace and KVM virtualization layers, custom hypervisor patches to implement this. The problem with this is it's not scalable in the cloud. So you need to have dedicated resources to leverage this technology. And ultimately, what we're kind of seeing is that when you use emulation-based fuzzing, it's going to be a bit slower. So it's better if you can scale horizontally. And to do that, you tend to need to put it in the cloud. OK, so just trying to wrap up here. I'm kind of out of time. But as I mentioned, GDB fuzzing, there was a paper just this year that kind of just talked about how you can apply the snapshot fuzzing approach to pretty much anything that GDB can attach to. And then when there's times that you can't instrument it and there's just you have a problem where you need to generate an indirect observability point. And we call that differential fuzzing. So you tend to create an oracle, kind of a third component that determines whether or not the behavior has been modified. So an example of this would be when people are looking for CPU bugs or bugs in disassemblers, they'll run the same code through multiple disassemblers, and of course we would expect the output to be the same, but if there's any sort of difference there, then you can detect bugs in the disassembler decoder, for example. This has been used to do smart contract fuzzing. It's a popular approach that, because the runtime environments for smart contracts need to be verifiable, if you can even cause a denial of service or timing delays, that can lead to cost and expense, and people are making hundreds of thousands of dollars finding bugs in the like Solana runtime environment, for example. Okay, so I am out of time. So in summary, I just want this to be an inspirational talk. Hopefully you can see that there's layers and layers of sophistication to fuzzing. You can spend your entire career there and find success and hit new targets. As we see the technology develop, it just unlocks more and more potential for the targets that we can hit and the value we can extract from this strategy. So look for me online. I do teach trainings, and thank you for your time. It was great to see you, No Hat.